In this video, we are going to learn about analytic functions. The topics we are having in this analytic functions are definition of analytic function, Cauchy-Riemann equations, properties of analytic functions, determination of harmonic conjugate, Millet-Thomson method. What do you mean by analytical function? Analytical function, also named as regular functions or holomorphic functions, it is defined as a single valued function which is analytic at a point z0 if it has a derivative at a point z0 and at every point in some neighborhood of z0. Note, if it is analytical at every point in a region R, then it is said to be analytic in that corresponding region R. The necessary and sufficient condition for a complex function f of z to be analytic. Here we are seeing the necessary condition. If f of z equal to u plus iv plus, here z is the complex variable x plus iy, is an analytic function in a region R of the z plane, then its first order partial derivatives dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y exist, and it satisfies the equation dou u by dou x equal to dou v by dou y, dou u by dou y equal to minus dou v by dou x at every point in that region. So here this ux equal to vy and uy equal to minus vx is called the Cauchy-Riemann equation in Cartesian form. Now, the sufficient condition for the function to be analytic is the first order partial derivative exists and they are continuous. So here we are having the statement, let f of z equal to u plus iv. We assume that f of z is an analytic function in a region R. Then by the definition f of z has a derivative everywhere in the region R. So f dash of z you can write it as limit f of z plus del z minus f of z by del z, where del z tends to 0. How to get the Cauchy-Riemann equations? To find it, we are considering z equal to x plus iy as the complex variable. Del z is nothing but that small increment del x plus I into del y. So by adding z plus del z, we are getting x plus del x plus I times y plus del y. So f of z plus del z is going to be u of x plus del x and y plus del y plus I into v of x plus del x comma y plus del y. So f dash of z you can find it from that. Then case 1, if del z tends to 0, that means you have to assume that del y equal to 0 and del x tends to 0. So by assuming in that manner, you are getting limit del x tends to 0, u of x plus del x, comma y, plus I into v of x plus del x, comma y, minus u of x, comma y, plus I into v of x, comma y by del x. So, by del x tends to 0, you can separate the real part and imaginary part. We are having this equation. So, this equation is representing the first order partial derivative of u with respect to x, and this represents the first order partial derivative of v with respect to x. So, f dash of z is ux plus I times vx. Case 2. By allowing del z tends to 0, now we are going to assume that del x tends to 0 and del y tends to, del x we are assuming it is equal to 0 and del y we are allowing to 0. So you are going to get this f dash of z is going to be u of x comma y plus del y plus I times v of x comma y plus del y minus u of x comma y plus I times v of x comma y divided by I into del y. By separating the real and imaginary part, you will get 1 by I into dou u by dou y plus dou v by dou y. So we are having differentiation of f of z, we are getting in terms of y variable, that is uy plus I times vy. Then from equation 1 and 2, we are getting ux plus I into vx equal to minus I into uy plus vy. Comparing the like terms, you are going to get ux equal to vy and uy equal to minus vx. Hence, we are getting the Cauchy-Riemann equation. Okay. Now, the Cauchy-Riemann equation in polar form is, if f of z is considered as u and v are functions of r and theta, is differentiable, and z equal to r into e power I theta, then dou u by dou r equal to 1 by r into dou v by dou theta, and dou v by dou r equal to minus 1 by r into dou u by dou theta. This formula is very important. Now see this example. You have to show that f of z equal to z cube is an analytic function. Given that f of z equal to z cube, so we know that z is x plus iy the whole cube. By making use of a plus b the whole cube formula, you are going to have x cube plus 3x square I into y plus 3x into iy the whole square plus iy the whole cube. Now, separating the real and imaginary part, you will get x cube minus 3xy square plus I times 3x square y minus y cube. Now, by separating the real and imaginary part, by considering f of z equal to u plus iv, you are going to have u equal to x cube minus 3xy square and v equal to 3x square y minus y cube. Differentiating u partially with respect to x and y, you will get ux equal to 3x square minus 3y square. Uy is equal to minus 3x into 2y. So that gives you minus 6xy. Likewise, differentiating v with respect to x, the first term is having the x term. So you are having 6xy. Second term is going to be 0. Differentiating v with respect to y, you are having differentiation of y is 1, 3x square minus 3y square. Now, checking out the CR equation, you are having ux equal to vy. See here, ux equal to vy and uy is equal to minus vx. So, CR equation is satisfied. Therefore, we can say that the function f of z equal to z cube is an analytic function. Likewise, you can check out the analyticity for the function f of z equal to e power z, f of z equal to cos z, and f of z equal to sine hyperbolic z. So, how to check out f of z equal to e power z? E power z, z replaced by x plus iy. Therefore, you are getting e power x plus iy. So, you can split this exponential e power x into e power iy, which is equal to e power x into cos y plus I sin y. Now, separating the real and imaginary part, we'll get u equal to e power x cos xy, cos y, and v equal to e power x into sin y. So, differentiating with respect to x partially, we are having e power x into cos y, and differentiating v with respect to x, you will have e power x into sin y. Differentiating u with respect to y, we are having the differentiation of cos y is minus sin y. So, minus e power x into sin y. Differentiation of v with respect to y is differentiation of sinus cos y into e power x. So, if you are seeing this, ux equal to vy and uy equal to minus vx. So, it shows that CR equation is satisfied. Therefore, f of z equal to e power z is an analytic function everywhere in the complex plane. Now, in this, you can able to find out the derivative of f of z. Next, cos z, function f of z equal to cos z. So, how to find this? Cos z is replace z by x plus iy. So, cos of x plus iy, it can be considered as cos of a plus b formula. Cos a, cos b minus sin a, sin b. So, cos x into cos iy minus sin x into sin iy. We know that cos ix is cos hyperbolic x and sin ix is I sin hyperbolic x. Therefore, here you are going to have cos x into cos iy is cos hyperbolic y minus I sin x into sin hyperbolic y. Now, separating the real and imaginary part, you will get u equal to cos x cos hyperbolic y and v equal to minus sin x sin hyperbolic y. Differentiated with respect to x partially. So, dou u by dou x will give you differentiation of cos x is minus sin x into cos hyperbolic y. Differentiating u with respect to y, you will get cos hyperbolic y differentiation is sin hyperbolic y because you know that cos hyperbolic x equal to e power x plus e power minus x divided by 2 and sin hyperbolic x is e power x minus e power minus x divided by 2. So, differentiation of this will give you d by dx of cos hyperbolic x is going to be sin hyperbolic x and d by dx of sin hyperbolic x is going to be minus or plus. Differentiation of this is e power x plus e power minus x. So, you are going to have cos hyperbolic x. Therefore, substituting the derivative of it, so differentiation of cos hyperbolic y is sin hyperbolic y and differentiation of sin hyperbolic y is cos hyperbolic y. So, substituting the differentiation value, we can able to observe that ux equal to vy and uy is equal to minus vx. So, CR equations are satisfied. Therefore, we can say that f of z equal to cos z is an analytic function. Next, we are having the derivative of f of z, that is cos z. You can able to get minus sin z in terms of this differentiation.